Hello, my name is Aliasghar. I'm presenting a paper named Safety Guaranteed Learning Predictive Control for Aggressive Autonomous Vehicle Maneuvers. The co-author of this paper is Professor Jingang Yi, and we are with the Department of Mechanical and Aerospace Engineering at Rutgers University. Motivations of this paper are securely maximizing the maneuverability of the autonomous vehicles. As you can see in the video down here, the vehicle is able to follow the trajectory containing aggressive maneuvers, which can be used for a safety feature in the future self-driving vehicles. We use nonlinear learning predictive controller to enable safety guaranteed aggressive vehicle maneuvers and polynomial-based Gaussian process to improve the models in real time, and sum of square method is employed to estimate the vehicle safety boundary in real time. You can see the architecture of the control is represented here. The motion planning of the vehicle is not the main contribution of this paper, but the main focus of this paper is the motion controller and the numerical learning methods. We first talk about the vehicle and then feedback linearization controller, model improvements, safety region, and how we use all of these in nonlinear model predictive controller to securely maximize the maneuver. You can see the 1 to 7 scaled vehicle we used for our test. We used the indoor racetrack and image processing to localize the vehicle, IMU and precise encoders on each wheel, and NVIDIA TX2 as embedded computer unit. The robot communicates to a computer at the edge using a Wi-Fi and ROS communications. To design the controller, first we have to have a analytical model of the vehicle, and the vehicle has two parts, the tire and the vehicle. The tire model is estimated by the slip ratio lambda for each wheel and the side slip angle alpha for each wheel as well. Magic formula is able to estimate the tire model by knowing the slip ratio and side slip angle. Slip ratio is the difference between the longitude velocity of the tire at the point the tire is contacting the ground and the rotational speed of the tire produced to the radius of the tire. And the side slip angle is the difference between the tire's direction to the velocity vector as direction at the point the tire is contacting the ground. The equation of the motion of the vehicle is extracted using all the applied forces from the tires and the rotational and angle and longitude and lateral acceleration of the vehicle. State space of the vehicle contains 10 parameters. The first three are the locations, x, y side. The second part, v, is the longitude, lateral velocity, and the yaw rate of the vehicle, v, and omega is the angular speed of each wheel. And inputs of the system are the steering wheel angle delta and the throttle Kc. And state space of the vehicle is presented as Fn here. To design the safe learning predictive control, first we initialize the models and then initialize the model polynomial based Gaussian process and initialize the sum of square to calculate the first security or a safety boundary for the vehicle. You can see the more detailed diagram shows here that the vehicle use feedback linearization, then inverse dynamic and nonlinear model predictive controller to find the inputs for the vehicle, which they are inside the safety region found by sum of squares. And the dynamic learning finds the new values for the vehicle's model and improves the modeling within the time. So the controller part contains two main blocks. The first one is feedback linearization control, and the second part is nonlinear model predictive control. Feedback linearization control finds the longitude and lateral forces of the vehicle in real time by the trajectory error E and the derivative of the trajectory following error E dot, and the part Vx and Vy are the uncertainty parts, which they include the longitude and lateral forces. By putting these inputs in the dynamic of the system, the closed loop control system looks linear. By having an uncertain part eta t, which is a time variant function, we can calculate or estimate that using polynomial based Gaussian processing. You can see here we improve the model of the tire by collecting more data. The improvement is 5 times more accurate by collecting less than 4 times more data in real time. And by improving the model, we should be able to calculate our safety region in real time. For calculating the safety region, we use sum of square, and sum of square converts the stability problem or Lyapunov stability problem into optimization. For polynomial functions, which we model them or represent them as CIVI, there is an optimization method called positive semi-definite optimizations. They are able to find the terms CIs for a polynomial-based Lyapunov function in a way that the Lyapunov function is always positive definite and the derivative of the Lyapunov function is always negative. And this definitions means if we start from any initial point x0, we will always stay inside the region showed by a capital R, which these are the basic definitions of Lyapunov function. As you can see here in the right picture, we estimated the safety region using a sum of squares, and it is shown in the left picture using analytical methods proposed in previous papers. The red rectangle shows the open loop stability for the vehicle, which we presented in previous works. We are able to extend the stability region by applying controller and estimating the stability region for the closed loop system. And these methods calculate the equilibrium points of the simplified bike model for the vehicle on lateral side slip angle and the yaw rate for the vehicle. So similarly, we represented the stability region on the face portrait of the vehicle for the side slip angle and the yaw rate. And the blue part shows the stable part here, and the light blue part shows the parts that they have uncertainty, but they can be stable if we reduce the uncertainty part and increase our model accuracy. And for formulating the sum of square, we use the closed loop control and we change state space into x dot, which is x is equal to the tracking error and the derivative of the tracking error, and f eta is the part that is the uncertainty part in the closed loop control system. We estimated f eta using polynomial based Gaussian function as we presented in previous slides, and we are able to formulate the sum of square optimization to find the stability region. By finding the stability region, we are able to apply that to our nonlinear model predictive controller and using that as a cost function panelized parameter. If the vehicle goes outside of the stability region or safety region, we panelize the cost function, and beside minimizing the tracking error and the derivative of the tracking error and keeping the changes in inputs of the vehicle, we will be able to keep the vehicle inside the safety region. We can see the experimental results. The vehicle is able to follow the trajectory in real time and the changes in the surface condition. Here there is a plastic surface with applied water to it, which has uneven friction surfaces. The vehicle is able to follow different velocity profiles, and the performance of the vehicle comparing to the cautious nonlinear model predictive controller and restricted boundary model predictive controller in the time wise and the agility metric wise They are both stronger. We are able to reach faster time lapse and reach to higher agility metrics, which the agility metric is the accumulated lateral jerk and accumulated relative lateral acceleration of the robotic vehicles. You can see the vehicle is able to reach to the higher velocity profiles and yaw rate profiles and stay in the larger value for longer amount of time. And similarly for the side slip angle and the steering wheel angle, the proposed method stays at larger value for longer amount of time comparing to the cautious nonlinear model predictive controller and restricted boundary nonlinear model predictive controller. And conclusion, MPC and FLC are able to help us to securely follow the trajectory. Learning-based methods improve the modeling, and sum of square finds the stability region in real time. And experimental results demonstrated the proposed method is performing better than existing methods. Thank you, and thanks to Alvor, Dimitri, and Joshin. Please ask any questions if there is any question.